always like either that you use the MEG in the clinical setting or in the research, you have to understand what you want to answer by using this technique. And I will try to go through it quickly today and more in depth in the next lectures. Okay, so as I said, I have experience with all these neuroimaging technique. As Javier said, there are so I'm very lucky because my research center is the best neuroscience center in Italy. I'm not saying that, or the statistics says that, and we have a dedicated research MRI facility, MEG and EEG. So as I said, I started using fMRI mainly, and then I also moved to MEG, EEG. Now I'm using them all in my research lab. And so I have also the unique idea of how to compare these different type of techniques one to the other. So as I said, I think that the main, and probably you already know, the main difference between the MRI and EEG, MEG is based on the type of information they give us. This will come also later, as MEG, EEG has a very high temporal resolution, so allow you to see how the brain processes information with a very let's say high temporal resolution, so at the level of a millisecond, whereas the functional MRI cannot show that. The time of the MRI acquisition of the entire brain is like 1 or 2 seconds, let's say, but even the signal that you measure with fMRI is very slow. So this is one of the first difference between the two, that the type of application that you can do are based and defined by the type of signal that you are measuring. And this is what we will see also later on. And also in terms of the question, for example, the research question that you can answer, they are in general very different, as fMRI cannot tell you how, for example, the information might flow in time in the brain, whereas MEG and EEG allow you to do that. So the things that you can understand with these different techniques is very different. Okay, this is just a general introduction. So in order to efficiently use a technique, you need to know what the technique measure and how you can use that signal to answer specific questions, scientific questions or clinical questions, if you're interested more in the clinical part. And for this, you need to know how these signals originate in the brain. Okay. So let's start with the first part. As I already anticipated, it's very important that you know how MEG works in order to optimize the things that you can and cannot do with MEG in terms of the type of studies that you can conduct with MEG, but also in terms of how you can treat the signal, so how you can analyze the signal in order to answer the question that you want to answer. Okay. So this might sound like strange to you probably, but the first thing that I always ask to myself when I find like a new technique, or I encounter some new studies or new technology that I don't know before, is this technique really useful for me? And to answer this question, this is not trivial. You need really to study a bit how the technique works and what you can basically measure with it. And if this measurement that you do, in this case, this type of brain signal, might be helpful for yourself. As I say in many times, this is particularly important for MEG, because we will see that the signal that we get from MEG and EEG is so rich, is so full of features, because it changes really fastly in time, that it's very difficult then to focus on the part of a signal that we are interested in. But we will go through this later. So this to start with how MEG works. So this is a typical MEG. similar to the one that we have in the at CIMEC. Actually is exactly the same because it's the same brand. So as you can see, the participant is within the MEG. Normally it is seated like if he is basically doing a behavioral study. So in this kind of upright position. There are some people that do some sleep studies. And so the MEG will be flipped down, and the person will be on a bed, and the head will be in this helmet where the sensor of MEG are, but basically laying down. But the normal setup is like this one, okay? So as in any normal signal, in any normal setup, you can basically watch screen and do some type of cognitive task as they do in the laboratory for behavioral studies. This is much more natural setup than in a magnetic resonance imaging schema. Okay, so just to show, this is exactly our machine, and within this helmet that you see here, there are some sensors that acquire the signal originating from the brain. We will see later on how this signal originates in the brain. You can see, for example, in our case, we have 306 sensors. There are different sensors that collect different type of information, and we will come in a second. So this is an example of raw data from participants. So I just took a screenshot of a study that we ran some time ago, and you can see that you can already see that there might be some channels that have some noise, for example, as you can see here, or some other channels that might have some type of data that might be changing through time and so on. But this is just the raw data. If you don't have any kind of very evident modifications, then or you're quite a good expert, you won't see much. But this is just to show you how it works. So the person will be in a specific room with the MEG. The sensor will record the activity, similar to what an EEG might do, even if the signal is different. And this will be the data that we are collecting. And then we analyze this data in different type of ways. In addition to the MEG data, this is again another type of example of fewer sensors. So just like 8 sensors of different type. We can collect electrooculogram. So we can put some electrodes on the eyes to control when the person is basically making a saccadic movement. And we can also collect ECG data. This is done for 2 main reasons. First reason is that having some external signal that tells us which might be the trial, for example, in which the person blinked or moved the eyes, is helpful to remove this data that might be contaminated by this signal. And also, for example, we can use the ECG to remove using a specific type of preprocessing algorithm this data from the data. So ECG is much stronger in with respect to MEG signal, and so it might contaminate the MEG data. So collecting this data might allow us to control for that data. So the very first type of way in which we can use the MEG data is similar to what we do with EEG. So we present some stimulation several times. I will make some example in the next lecture also, but also today. And we can have a lot of time the very same type of stimulus. So we can have condition 1 and condition 2. And we have 100 trials for one condition and the other. We simply extract the part of the data around this event, and then we make the average across all these trials, and we can compare the different type of condition. Okay, so let's say that we have data from condition 1, and there seems to happen something at this time point, and we see that there is a change in the signal around that point. We might be interested in understanding, if we have two conditions, how they might be different. In this case, like a study on different type of words conditions, and we can see that averaging a lot of trials for the two conditions shows that there might be a difference in these different type of peak. And this is one way of using MEG to try to understand what is happening in the brain. If we have already an idea of what these different peaks might mean, we can try to infer how the condition that we decided before running the experiment might basically affect the signal. So there might be differences in terms of the sensory modality that we use, or there might be more higher order differences related for semantic aspects of the words and so on. And then we might find specific modifications in terms of the intensity of the signal at different time points. And we can infer from that by seeing where this type of difference is, where in the brain this type of information might be differently represented. So this is one of the first way of analyzing the signal from MEG, and is very similar to what you do in EEG actually. Clearly, as we see later, MEG records differences in terms of magnetic field modification and not electric field. So in this case, this is not an evoked related potential, but is an event related field, because as you can see from the unit here, the signal is in Tesla. So what the sensor in the MEG we capture and we will see later is related to modification in the magnetic field that is generated by the electrical activity of the brain. So this is just the easiest way of using MEG to try to figure it out how the brain works. Okay, and it's basically by comparing the average signal across several trials for different type of conditions. But as I said, MEG has such a rich type of signal that we can look at the signal in a different way. Okay, see, this is just to show you that clearly here we are considering just one of these 300 sensors, but actually there might be effects that are just limited to some specific type of sensor in the brain, and this makes our analysis much more complicated, because we might also have a specific type of hypothesis related to where in the brain the signal might change. And there's a way of showing this type of modification in terms of topographical maps. So showing where the information, so the signal might be different with respect to two type of conditions, for example. And we can depict these in these ways, by showing, for example, where one condition might elicit a stronger activity or a smaller activity. That is very similar to EEG. So I think you already have seen this kind of picture, but the main point that I want to make here is that the signal that we record is different. So as we will see later, this type of topography, if we do the same type of study in EEG and MEG, will be different, because EEG and MEG capture a different signal from the brain. We will see an example later on. As I said, the beauty, but also the difficulty of analyzing and using MEG is that MEG, with respect, for example, to fMRI, has this kind of high temporal resolution, which makes the data that you analyze very complicated and very complex from the temporal point of view. It's like you have a photo of the brain like every millisecond or every few milliseconds, whereas in the fMRI you have just a nice picture, but that is related to 1 second. So let's say that one way of trying to show you that the signal that we are looking at is much more complicated is not to look at the data in terms of the signal that we can average across different type of trials, but is to extract the power, so the intensity of the signal across different type of frequency. So in this case, what you do, you extract, as before, the time period you are interested in, and you extract from this one, so you extract the intensity of the signal for the different time frequency. So I will go through this with an example. So in this case, for example, I'm taking some data from one of my study, and I'm interested in how the brain represents the action we want to do. So if I'm looking at the data that is extracted like here, so event-related field, I don't see much into the brain, even if I know that the people are engaged in a very complex task. So normally what I do is to extract the intensity, the amplitude of signal at the different frequency. So to decompose using like Fourier transform in order to extract the power for the different frequencies. So in this case, for example, the task is very simple. At time 0, we have a queue that tells the participant the type of action it will have to do. And then we have a go queue here. So this is like a go, no go task. And if we tell here the participant to move later on, you see that after the signal go, you have quite a change in different type of frequency. This change might be negative with respect to the baseline or positive. And changes at different frequency range seems to have a different type of meaning in terms of the type of processing that is happening in the brain. So at the moment, it's not important that you understand every modification in terms of the role of these frequency in the brain, but what you need to appreciate is that even during this delay in which the participant is doing nothing apart from selecting the type of action that it has to do, you see that there are some modifications in the brain. And these modifications are also different at the time where the person is doing something, okay? If I will use fMRI to study this, and I'm using it, I will have all this very complicated information just compressed in one fMRI scan. So I will have just one brain. Whereas in this case, you see, I have the evolution in time of how this information might change into the brain. And this is the power behind MEG and MEG that normally people don't understand. So this is the beauty, but at the same time, it's very difficult then to approach this type of analysis and this type of data if you don't have a very good hypothesis of the type of signal that you want to look at and of the information you want to extract from all these type of information, okay? Just for me, are you already familiar with this kind of time frequency analysis and representation or not?
No, they are not, but they are familiar with the EEG analysis in time domain.
Okay. Okay, so is the same things that I'm saying now is important also for EEG to a similar degree. There are some differences between the two techniques. We will arrive to this difference later on. I think it's always important that before knowing how you get the signal, as you already know EEG, it's good to understand what you can do with this data, okay? And for me, the first time I've seen this kind of representation, as before I was using just fMRI, for me it was amazing how much information was captured by these techniques, something that before I couldn't see with fMRI. And as in cognitive neuroscience, we are interested in understanding how the brain processes information, and time is a crucial aspect of this. For me, this type of representation represented like a new starting point for my research. Up to now, I mainly described to you information that can be extracted with the specific sensor. So as I said before, the participant is inside this sort of helmet, and we are recording the information from this specific sensor, and we analyze the data here. But powerful approach of MEG and also of EEG up to a certain point is that we can use what is called source analysis, which is an analysis that allows us to project the data from the sensor here, that is where we collect the data, into the brain to see most likely where these change have been originating. And this will lead you to maps that are very similar to the one that you see with fMRI, but which tells you which type of neurons and a large population of neurons actually originated what you recorded on the sensors. And this is called like source analysis. You can do source analysis of the time domain data, so of the event-related feed that we've seen before. You can do MEG analysis of the frequency domain, so looking at where changes in power have been originated. And this is very powerful because it allows you also to compare the possible similarities and differences with signal that you, for example, can measure with fMRI. One last very peculiar and very powerful approach that we can do with MEG and also to lesser extent to EEG is that we can also project the data in specific brain areas we are interested in and see how these specific areas might have originated the signal that we record from the brain. So I'm trying to go a bit more in depth in this. So in this case, what we do is we find an effect on the sensor and we look where it's originating in the brain. But let's say that we want to understand in a specific type of task, what is the role of some areas within the inferior frontal gyrus, ventral premotor cortex. We can simply make an analysis, which is called virtual sensor analysis, that projects the data that we record from the sensor into the brain and will basically show us how that brain area would basically respond to the stimuli. And then from this type of signal, we can also perform time frequency analysis. So the advantage of MEG with respect to EEG, and we will see this later on, is that MEG is much more powerful in this because the signal that it records is basically not distorted by the brain, whereas EEG, so electrical signal, is basically distorted when it is recorded at the sensor level. And we will see this later on. The final aspects for which we can use MEG and EEG is also to understand how the brain might communicate information in time. So, and this is one of the most powerful and most important application that I think distinguish MEG and also, as I said before, beat EEG with respect, for example, to fMRI. First, we can understand how the information within the brain might change during time, but also we can estimate how two areas within the brain might communicate differently in time. Again, we can do this by making the calculation based on the sensor, so on the data that we record directly from the MEG, or we can project this information into the brain using what is called source analysis. And we can look at, for example, two areas, one parietal and one frontal areas, and understand how these two areas might communicate in time. And this is something that is basically not possible with fMRI. It's possible to understand how these two areas might communicate, but given the very low temporal resolution of fMRI, we cannot see how these communication evolve through time. We can have just have a snapshot of what is going on, and that's all. So already from all this presentation, I tried to make you understand what are the very important strong points of MEG and how we can use these kind of feature to basically use this very rich signal in order to understand how the brain works. As the last example of this, I'm also simply touching fastly the most advanced type of analysis that I'm also doing in my studies. This is very common, for example, in fMRI. So, and it's based on a multivariate approach. So instead of simply comparing, for example, the activity at the level of the event-related field or in the frequency domain of two conditions, I'm not going into the detail of how we can compare the pattern of activity within two conditions and see if this is different or not. This will lead us to have some decoding maps which tell us how information is represented in the brain at a specific time point, and we can do this analysis in sensor space or source space. And this, for example, a study that we conducted some time ago, and you can see, for example, here that in the figure, instead of plotting the power change as we've seen before, we plotted the decoding accuracy of our classifier in a specific type of, in a specific sensor in the brain. And we can see that there is this kind of significant decoding in this time period. Whatever it means at the moment is not important. What I want to show you is that this temporal dimension is particularly important also in the case when we use this type of approach that allow us, for example, to distinguish how specific type of object categories might be represented in the brain and how different parts of the brain might represent the same type of information at different time points. And this is crucial to understand how, for example, specific brain networks might work and how the information within brain network might be basically moved along the network and how can be this information can be transferred at the different time point of the of a task. So this, for example, approach is has been widely used, for example, in working memory studies in order to understand when and how the information that we store in working memory might be represented and in which part of the brain. And that is something that it really suits the type of approach and analysis that MEG and EEG can do. So again, I make an example with fMRI. With fMRI, it's very difficult. So there are a lot of studies on working memory, for example, but the problem of working memory is that you need to show, for example, a specific type of stimulation, then you give a specific time of delay in which the person has to retain that information. And then you show another stimulus that might be the same or not the same that you shown before and ask the participant to say is the same or not. In that specific case, the interval between the initial probe and the test stimulus is the part that you are interested in. But with fMRI, it's very difficult to dissociate that specific time period because normally you put everything together and it's different to understand what might be really related to working memory. Whereas the studies using, for example, EEG and MEG have started unveiling how this type of information might be represented during this delay and really provided novel evidence about how the brain might represent this type of information. Again, you don't do this kind of advanced multivariate analysis on the sensor level only, but actually you can also see where this type of information might be represented, again, with source analysis. A very advanced and recent and debated use of MEG. So If you come to us and I will show you the MEG lab, I will have some photo later on and you will see what it is. The first thing that the technician will tell you is you cannot take any mobile phone, any metal object inside the MEG because this will distort the signal. So normally they will tell you that it's not possible, for example, to use a stimulation of the brain and at the same time record the MEG. Actually, in recent years, it seems that this is feasible. You need specific type of analysis, and I'm just showing you here recent study already 10 years ago now that basically showed that it's possible to do TDCS, for example. I guess if you're not familiar, there is a current generator. You have a positive and a negative electrode, and you make a low electrical current pass through the two electrodes, and these change the excitability of the brain and possibly have also effect at the behavioral level in specific type of task. In this specific case, what they did was to show that it was feasible to measure MEG signal even during this type of stimulation. If we have time, I will show you a specific example. But this is just to show you that potentially you can use MEG in combination with other technique, even online, whereas this in the past was considered as impossible. Okay, so after I've shown you how you can really use the information about MEG and how rich the signal that you record from MEG is, as you see, I've shown you already 4 or 5 ways in which we can basically analyze these type of information. And the question is always the following. So do I really need MEG to answer the question that I have? And this is something that both as a clinician or in my case, an experimenter, you will always to ask you. So is the type of a question, in my case, experimental question that I want to answer need MEG? If the answer is yes, in some cases it might be no. There might be questions that can be answered very easily with a behavioral study or with fMRI or with other type of analytical tools. If you think MEG is a good tool for you and it might be very good for answer what you want to investigate about the brain, then given that all the type of analysis that I've shown you up to now, the first thing that I always suggest to my student is take a time, think about what is the question you want to answer and what type of signal you might use from MEG to answer your specific question. Because the signal is so rich and so complex that you might go on analyzing the data for years if you don't really specify what is the signal in the brain that you want to see as changing based on your experimental question. Okay, so this was the first part in which I tried to introduce what we can do with MEG. Do you have any question, or do you think some parts were not clear so that I can go through it again? And then we can go more on the general introduction of the signal, how MEG lab is basically constructed, and what are also the implementation that we will see in the future of MEG.
Do you have any question, concern, comment, suggestion? No? Okay.
If I'm going too fast, just let me know.
No, I think it's okay.
Okay, great. Okay. So do we want to make a small pause now and then restart, or as we started later, I can go on?
Do you want to have some minutes? Yes, they
Okay.
want to.
No,
They want to
also because it will be intense. So I guess it's better if they do 5 minutes to, you know, to relax a bit, and then I can go on up to the end.
Okay, how long? 5 minutes?
Yeah, okay.
5 minutes, 5 minuti,
Ok.
5 minutos.
Ma cioè, va bene?
Sì, sì, un attimo che ti scollego da qua.
Ok.
Ah, ecco, ti ho perso dove sei.
Ci
Ecco,
sono?
sì, sì, ci sei, ti avevo
Ok.
perso per un attimo. Sì, tutto bene.
Tu tanto le
Ehm,
vigilie avevi già fatto, quindi, cioè, nel
Sì,
senso,
loro in realtà loro hanno studiato IG perché loro, questa è la seconda volta che loro sono con me, l'anno scorso hanno
Ah, ok.
frequentato la lezione di
Che alla
psicofisiologia e
fine
piano.
io lo faccio anche al quarto anno, che è più o meno il tuo terzo, secondo me, cioè alla fine mi piace anche dirgli un po' come possono, cioè, secondo me la parte più interessante è anche che se uno lo vuole usare deve capire come funziona, in termini proprio di cosa ci puoi fare, ecco.
Sì, sì, infatti,
Però non ho capito se
la
loro sono
settimana
anche più...
scorsa hanno fatto una cosa più pratica, quindi hanno fatto l'analisi IG, perché poi ormai sapevano già
Mhm,
come fare la registrazione, il recording e anche
mhm,
avevano visto dei dati ma non li avevano mai analizzati, quindi
mhm.
ci hanno
Ok,
provato un po'.
ok. Perché io poi domani, cioè, diciamo, nel prossimo avrei anche degli esempi di esperimenti, gli spiego com'è l'analisi e così. Cioè, quindi secondo te, cioè, va bene, è troppo avanzato?
No, va bene, infatti hanno fatto così per tutte le lezioni che avevano fatto tutte le neuroimmagini. Vedevano prima come funzionava la tecnica, dove si poteva usare, e
Mhm.
poi soprattutto nella parte più, diciamo, event related, sia dell'FMRI, dell'IGI, della NIRS, avevano visto anche come si fa l'analisi
Ok,
dei dati.
ok.
Anche se poi non ci avevano provato a fare tutte le analisi, hanno
No,
fatto
vabbè,
solo
ma
la pratica
quello in
FMRI.
realtà, cioè, domani provo a spiegargli un po' di cose, cioè, venerdì, scusa.
Sì, sì.
Vediamo poi dove
Sì,
arriviamo. Eh?
non spaventarmi dai domani, perché sì, non devo cambiare tutto un'altra volta, hai visto che è un po' un casino. Quindi.
No, va bene, dai, insomma, oggi gli faccio vedere anche cioè, diciamo, quale sarà il futuro della Meg e cose così, che secondo me è abbastanza interessante, perché adesso ci sono dei nuovi sviluppi abbastanza, cioè, abbastanza...
Senti, mi avevano raccontato di una proposta di ingegneria che avevano fatto invece di fare tutto sai, quel caschetto per la Mac,
Sì, sì,
hanno sviluppato dei sensori modulari,
ne
diciamo,
parlo alla
che puoi
fine,
fare.
ne parlo alla fine della lezione.
Ah, ecco, sì, lo hanno fatto, e non è una cosa che mi hanno raccontato su Aliata, no?
No, no, guarda, ne parlo proprio alla fine perché, diciamo, la Meg probabilmente scomparirà a un certo punto.
Ma che triste.
No, 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 nel senso che verrà sostituita da quest'altra, da questi altri sensori a cui non serve l'elio liquido. È
Ma
una
quello
Meg,
costa molto di meno, no?
eh sì, appunto, costa di meno e il segnale è migliore.
Mm.
Quindi, vabbè, questo è il futuro, cioè, diciamo, adesso ci sono degli studi, ne farò vedere uno su Nature, il primo, che è di 3-4 anni fa,
Mm.
che fanno vedere come funziona e adesso ci sono alcuni gruppi nel mondo che la stanno sviluppando, è ancora in alfa, cioè non lo puoi, cioè, se la compri te la devi fare tu praticamente, ok? Puoi comprare i sensori, ma fra 10 anni, secondo me, e secondo un po' tutti, sarà lo standard.
Beh, in teoria noi abbiamo un centro di alta tecnologia che ce l'abbiamo qua nel campus dove dovrebbero sviluppare tutti questi tipi di cose.
Ma
Ogni
guarda,
volta che con loro,
in quel caso lì
io
basta
dico a
che
loro,
comprino i sensori, poi ti faccio vedere. Ci sono 2 startup che li stanno commercializzando e li sviluppano insieme a alcune università praticamente.
Sì, ho provato a fare la proposta con quelli perché qua noi abbiamo sia la laurea in tecnologia, sia il master e il dottorato.
Ah,
E
ok.
avevo proposto ai colleghi appunto di farlo, cioè di fare lo sviluppo di strumenti che ci servono per la biomedicina, per le neuroscienze. Ma ogni volta che parlo di questo loro mi guardano così come, ma cosa dici? Noi vogliamo fare delle macchine. Io, cioè, abbiamo un istituto di alta tecnologia, cioè le macchine non sono alta tecnologia.
No, no,
Però
boh,
vabbè,
guarda,
ogni volta
questi
che
qua, ti
chiedo,
dico, questi qua adesso, beh, dopo lo farò vedere alla fine, comunque ti compri i sensori, il problema è che chiaramente adesso ti vendono i sensori, cioè non è che, cioè, non è come quando ti compri le EG che hai, capito, tutto implementato, cioè è un sistema che tu premi un tasto e lui registra. Lì ti
mm,
devi fare il software tu, devi farti tutto tu, perché praticamente non c'è niente di commerciale, capito?
sì, ma anche una cosa, c'è buona fino a un certo punto,
No, nel senso che appunto ci sono
è
due o
anche
tre...
buono in realtà, perché ti costa
ci
meno e
sono...
puoi fare anche la patente.
No, no, infatti cioè, ci sono dei gruppi che vivono su quello, cioè sono gli unici al mondo che fanno questo e stanno prendendo un sacco di soldi per fare questo, capito? Le stesse università fanno la startup per poi vendere i caschetti, ovviamente,
Vedi,
perché alla
sarebbe una
fine...
buona idea. Lo proporrò ai colleghi, vedremo se
Guarda, tanto
qualcuno...
ti mando un po' di cose. Alla fine, al momento ci sono due grossi, cioè due ditte che stanno facendo sta cosa e gli studi glieli fanno l'università, poi sai, cioè gli stessi ricercatori sono dentro le start-up.
E voi lo state facendo? State
No,
facendo
no,
qualcosa con
magari.
qualcuno?
Noi volevamo comprarlo,
Mm.
questo qua che ti faccio vedere alla fine, per quello sono informato, ma al momento ce l'hanno sconsigliato tutti perché dovresti avere un gruppo di fisici, ingegneri full time che ci lavora.
Sì, infatti il vantaggio è che qua ce l'abbiamo, ma ti dico che tutti vogliono fare delle macchine, quindi...
Mhm. Guarda, vabbè, poi ti mando un po' di link, un po' di cose. Cioè, se voi, se a loro interessa, cioè i sensori li fanno, cioè compri i sensori e quello che dovresti fare tu è fare tutto il software e testarli, capito? Ma i sensori li produce una ditta da cui li compri, ecco.
Sì, chiederò a una collega che non mi ricordo dove aveva lavorato, perché anche lei fa la MEC, ma in un altro centro di ricerca. Mi aveva un po' parlato di questo e magari ci mettiamo d'accordo con lei e proviamo a trovare degli ingegneri e programmatori e tutto quanto che ce li abbiamo qua perché condividiamo lo stesso campus, quindi è
Guarda,
praticamente un
dopo io
campus di tecnologia.
un po' di informazione ce l'ho già dentro la presentazione.
E se poi
Ti
se
mando
puoi
un po'
condividere
ti
con un
mando, guarda,
collega.
ti mando, c'è una bellissima review di quest'anno che parla proprio dei vantaggi, quindi a livello anche, sai, di segnale, e poi ti mando un paio di link su chi li sta sviluppando, così.
Ottimo, ottimo. Anche così possiamo anche chiedere, fare domanda per qualche bando, che in teoria ogni anno dovrebbe uscire un bando qua e quindi potremo farlo. E se siamo un
No, poi
gruppo
sai, se ti
grosso è
interessa
difficile
comunque,
di
cioè, e voi avete, cioè, il nostro problema è che noi non abbiamo una cosa di ingegneria che fa quello, capito? Cioè, che fa roba biomedica e quindi, cioè, noi dobbiamo comprarci il sistema finito.
Sì, no, noi ce l'abbiamo, cioè si possono sviluppare qua delle cose che servono anche per i dottorandi e quelli che
Mhm.
ci interessa. Abbiamo anche un dottorato in ingegneria biomedica, quindi
Noi quello non ce l'abbiamo, ad esempio, non c'è, qui a Trento non c'è. E quindi
sì,
quello è
il
un po'...
problema è comunicare con loro, no? Perché sempre sono troppo messi nelle loro cose e poi ci ascoltano poco. E quindi
Certo,
dobbiamo finire per comprare tutte le cose con le aziende che li vendono costosissime, quando
certo, sì,
abbiamo
sì.
anche la possibilità di produrre tutto quanto qua
Mhm.
con i nostri gruppi. Però vabbè. Possiamo continuare allora?
Sì, vai, vai, vai.
Un attimo che ti collego nuovamente. Eccoci, ci siamo.
Okay, so we can
Allora un
restart.
attimo che non ti sento.
Eh, okay.
Ora ti sento. Mhm.
Okay, so normally people start from this part. So showing you what you measure with MEG and so on. But I prefer to start with what you can do with something and then explain you how it works, because I think it's more interesting, at least for me as a researcher. It's very interesting to understand the potential of a tool that I can use, and then to understand exactly what it measures and what the signal that is acquired from these tools is originating in the brain. So I guess you're already familiar with how the neurons communicate in the brain. So there are two main type of signal that might be the origin of the MEG, so the signal of MEG and EG. There might be, and it is not, action potential. Action potential, the structure of the signal is very fast, you know, even if it is very strong. And so action potential are not the origin of the signal of MEG and EEG, but actually postsynaptic potential are the signal that somehow are originating the signal that is measured using MEG and EEG. Why this? Even if the average amplitude of a signal is lower than action potential, the activity of postsynaptic potential is much more longer. This allows thousands or millions of neurons postsynaptic activity to be summed up together in time, and so that we can basically record the activity of quite synchronized, let's say, neuronal populations using these type of technique. So just to go a bit more in details, particularly not all postsynaptic potential are possibly the signal that are mainly contributing to MEG and EEG signal, but actually the main contribution of this signal is due to postsynaptic potential, so PSP, that originate from pyramidal neurons in the cortical columns of the cerebral cortex. So here you have an example of the signal that travels through the axons, and then we have the secondary currents and the primary currents. So primary currents are indirectly originating the signal that we measure with MEG as the change in the magnetic field induced by these primary currents is what is measured basically by MEG, whereas these secondary currents, so the change in voltage due to these secondary currents is what is mainly originating the EEG signal. So just to see this in another way, when the information basically travels across the axons, this is like the current that is traveling along the axon, and the current itself generates through the law by Biot-Savart a magnetic field that is basically recorded by the MEG, whereas these secondary currents along the axon are basically what is measured by EEG. Just very simple, but there is a difference between what you are measuring with EEG and MEG. This is due mainly to secondary current, whereas in this case, this is the magnetic field that is generated by the primary current. Okay, so it's not that, as I said before, all the neurons in the brain that are generating or contributing mainly to the signal that we can record with MEG or EEG, but mainly are pyramidal cells that are present in the cortical cortex. So, and as you can see here, particularly in MEG, the signal that is mainly represented is the signal that is perpendicular to the skull, because the one that is the one that is parallel with the skull, so the one that is basically in the sulci, so these type of cells that are oriented in these ways. Because in these ways, the magnetic field that is originated, that is the one in green, basically pass through the sensor. And as it changes through time, these changes might be recorded by the sensors. Due to simulations, we know that depending on the type of simulations, that should be around at least probably 50,000 or even 100, 200,000 neurons that should basically respond together in order to give rise to the technical signal in MEG. Why I'm giving you like an interval? Because depending on the type of simulation, this type of number seems to change a bit. Why these numbers might be important? Because these numbers also define the minimal spatial resolution that we can measure with the MEG. So the point here is that understanding how many neurons should basically respond together with respect to a specific stimulus in order to have a type of signal that is measurable by our MEG, basically will allow us to understand the minimal part of the brain that we can basically measure. So this type of intrinsic spatial resolution of the signal seems to range between 1 square millimeter and 1 squared centimeter. This is very important because for these type of numbers is much lower in the MEG, also because the magnetic field is not distorted by the medium. So the magnetic field originating from the brain while is passing through the liquor, the meninges, the skull, and the skin is not basically distorted and can be recorded by the sensor, whereas for EEG, the electrical signal that is originating from the neurons of the cortex is actually distorted by the cerebrospinal fluid, by the meninges, by the skull, and by the skin. So this is why, in general, the intrinsic spatial resolution of the EEG is much higher, so it's much less precise with respect to MEG, and why MEG is normally considered as much more better in terms of the type of spatial resolution information that can be extracted from it. So I just wanted to give you this kind of representation to make you understand that first, MEG measures something different from EEG, and in details, MEG records signal related to the magnetic fields changes that are induced by the electrical activity of mainly pyramidal neurons in the brain, and mainly pyramidal neurons that are within the sulci. In order to appreciate a change at the level of a sensor, we need to have 100,000 or tens of thousands of neurons that needs to be recruited in a synchronous way. The type of signal that is originating, and it is the main determinant of what we recorded at the level of the sensors, is the postsynaptic potentials of pyramidal cells. So it's not the action potential that is what we measure with MEG and EEG signal. Given the fact that we can basically record information that is related to this change of neural population responses, we can record the information at the level of milliseconds. As I said, this is a very good thing related to MEG, but it poses also strong limitation for the analysis that we want to do. So I'm trying to rephrase this. the fact that we can basically see the signal of the brain changing at the millisecond scale is great, because this will allow really to track on time what the brain is doing. But at the same time, this creates a problem in terms of the data that we have. So the data is so rich and so complex that sometimes might be difficult to handle in terms of the, in specific case in which we have very complex type of analysis that we want to conduct, or in the case that we have a very long, for example, experimental paradigm. The other advantage of MEG with respect to EEG is that, as I just anticipated, the magnetic signals are not distorted by the medium they pass through. So this allows that MEG has much better localization with respect to EEG. We will see tomorrow some examples with some simulations in which you can already see that EEG signals might be distorted and show some, let's say, activity within the brain when we look at the source that are basically generating the signal that might not be actually true. So when we do simulation of source analysis, we know exactly the data we are creating, and we try. So in the brain, we generate one activity, and then we make a simulation to pretend that we are recording that signal from the sensor, and then we can go back from the sensor to the brain, and we should see the same stuff. In this case, we know the ground truth. And if you do the same type of approach with EEG and MEG, normally MEG is much better than EEG. If you don't have for EEG, for example, the anatomy of a participant, and you use very complex type of model in order to go into source space. So this is one of the main advantage of MEG with respect to EEG. As I said before, as the signal that is measured from MEG is the change in magnetic field originating by the activity of the primary current. The activity that is mainly captured by MEG is the one in the sulci of the brain, in which the orientation of the current is parallel to the skull, whereas the one that are perpendicular to the skull are basically cancelled out in the sensor. So for this reason, the MEG has a slight, say, preference for activity in the source side. The advantage of, I mean, this is not really a big issue, because the brain is not a sphere, but is very convoluted. So there are very few parts of the brain that are completely perpendicular to the sensor in this sense. Okay, so one problem of the signal is that the MEG and also the EEG signal is very low in intensity with respect to the external environment, and even the internal signal of the body. For this, we need to place careful approaches in order to avoid that possible artifacts and that noise might contaminate our data, and these might be the type of noise that we can have might be endogenous. So for example, as I said before, also for MEG, we might have some type of activity related to some muscular activity that might contaminate our data, or the art activity, so like electrocardiogram or movement of the eyes that might strongly impact our data, or this is something that normally people don't consider, but if you are pressing your feet very strongly, you will have like artifact in data and so on. Clearly, there are also external type of causes that might, so exogenous signals that might basically contaminate our data, as you know, like the 50 Hertz, that is the frequency, the activity of the electrical stuff that we use in everyday life. Then we might have a specific type of problem related to the electrodes or other type of noise. This is just to tell you that this type of information should be removed. There are a lot of ways of removing this type of information, but the best way is always to try to avoid this type of noise in the signal if possible. Okay, I'm just going also briefly through the history of MEG. You will see that the history is quite short, in the sense that the first type, so the first type of MEG machine is much more recent with respect to EEG. So as you already know, I think there were in the last century the first studies that, for example, showed the possibility of collecting data related to electrophysiological signals like the electrocardiogram. So Einthoven measured it and also got a Nobel Prize for his studies, for example, or as you probably know, in 1924, Berger measured the first EEG, as you can see here, for example. But MEG came much later. The first recording was conducted in the late 60s at MIT, and they created this massive chamber in order to isolate the participants with respect to the magnetic field of the Earth. So this was the first MEG recordings settings, and it was just one channel. It was not based on the type of technology that we will see later. This was a resistive magnetometers. The data that were collected were 10 minutes. They averaged the 20 minutes, and what they see was something like this, which was something reminiscent of an alpha rhythm, from what you know. So the signal was very noisy, and they had need to like average like 10 minutes to see something. And this was acknowledged as the first measurement for MEG. It was in 1968 by Cohen and colleagues at MIT. Few years later, the same group made the first recording using superconducting magnetometers, which is the technology that nowadays we use for MEG. Okay, so this just to show you a bit how the signal that we measure is with respect to the activity of the brain. So just to give you an idea, this is in Tesla, and this is like 10 at -14, and this is around the intensity of an evoked field. Around here we have 10 -13 is the activity related to alpha. So this one that you just seen, just to make you an idea, the type of intensity of the heartbeat is like around here between like 10 at -10 and 10 at -11. So the signal is 10,000 times, so 10 at the 4 or 5 bigger. So just to let you understand that even the internal signal of the body is much greater than what we are measuring. So we need to isolate the chamber where we are recording the data from the activity of any kind of possible source of noise from outside. So just to show you, for example, if you have a car moving at 50 meters from the MEG, this signal is way higher than the one that you are collecting. And if you don't have any ways of shielding the place in which you are recording the signal, you will see nothing. So just to make you an example, when we do experiment and we record the data, we are very lucky because our center is in a very in a place of the city that is like a small village, so it's there are very few cars that pass by. Most of the people that have a car just work in our center, and they go away around maybe 5, 6, and around the time where everybody lives. And if you are doing like a study, you will see some kind of change in the signal that you can filter out later on. But you basically see immediately some car is like passing by at 10 or 20 meters, because that signal is much more stronger than the one that you are basically recording there. This is why I'm showing you this type of scale. So just to show you the magnetic field of the Earth is also like 10 elevated at around 9, so 1 billion times bigger than the signal that you are basically recording and interested in. So this is why you also need a specific type of chamber that we will see later that needs to isolate your recording site from the external magnetic field of the Earth. This is just to show you the type of things that I just shown you here, but showing you the intensity of the signal at the different frequencies. Okay, so I just tell you that the type of technology that all the MEG are using is the same in terms of the way in which the sensor acquire the data, but there are different type of sensor for different type of MEG. We will come to this later. Okay, I've shown you before the setup. So this is the setup, and people are basically sitting in the MEG with a head here. Inside this helmet, there is what is called the dual. So this part here, that is basically a container in which there are the sensor. These sensors, in order to work, are basically within a solution of liquid helium, which is at around minus 200 degrees. Because with this type of temperature, the sensors can capture the changes in such small changes in magnetic field that are originating from the brain. So these superconducting quantum interface devices are called SQUIDs. So this is like each specific electrode has a single SQUID, and we have like 300 SQUID in our MEG system. How it works? These are the sensors that are depicted here, and they record the magnetic field changes at this stage that are originating from the brain. Okay, as I said before, this is the direction of the currency along the pyramidal neurons, and this is the induced magnetic field that is captured by this sensor. As I said before, if the sensor is basically here, these are the neurons that are originating the type of a magnetic field that is basically captured by the sensor. Okay. As I told you, the activity of brain is much smaller than the magnetic field. So
Okay.
if we are, yeah.
Okay, we have a question.
Yeah.
Pero no tiene micrófono.
Can you hear me? Yeah.
Okay. Here, just a second.
Sure.
Hey, sorry, why the liquid helium again? Why do we need
Okay,
the
so
liquid helium?
this is like in order to function, this sensor needs to be below a certain temperature, because the type of activity, so in order to work, they need to be at that type of at temperature, because in this way the sensor works like a superconducting agent, so it can capture this type of changes. Okay, so it's very complicated in terms of physics, and I honestly don't know all the details about it. The point is that in order to work, there needs to be like in this liquid helium. The problem is that as it is at this very low temperature, it evaporates, and you need to basically add the helium. In our case, for example, every week we have to change and put again new helium inside, because it will basically evaporate. If you don't have the helium, the sensor will not work. Okay?
Okay, thank you.
So, and this is the only, sorry, the liquid helium is the only danger you have in the MEG. So it never happens, but potentially, if the dewar breaks, then the liquid helium will basically come in the MEG lab, and will basically pass from the liquid to the gaseous form, which is at the normal ambient temperature, and this might pose a problem in terms of, because it will basically expand. Normally, this doesn't happen, because this is why the dewar is basically constructed. One disadvantage of having this dewar is that you have a distance between the sensor and the scalp, okay, which is due to this kind of security stuff. As I said before, this type of superconducting sensor allow us to record this very small change in the magnetic field, which is not possible with normal sensors. This is why you need basically the helium, okay? Even if you can record this activity, this is not enough. You need also a specific setup in order to record it. You need a magnetically shielded room. In this case, you can see like this is the door. So you will close the door. There will be a way in which the door is basically hermetically closed, and in this way, the idea is that the MEG is at the center of this room, and so you can basically, the shielded room allow us to minimize the effect of the magnetic field of the Earth with respect to the site of recording. So the idea is that with the squid, given their specific technological development, you can basically record changes in magnetic field that are so small, like the one originating with the brain. But this technology alone is not enough. You need also to seal the room in which the recording are done in order to do that. So just to give you an example, this is the range of the Earth magnetic field in different parts of the Earth. So in our site, this is the value of the Earth magnetic field, which is around 40 microtesla. And the brain activity, as I've shown you before, is like 10⁹ times smaller than this. So the idea is that with this magnetically shielded room, we managed to somehow confine or minimize the effect of the Earth magnetic field, and then we can basically have a much less distorted signal in the center of the room, okay? This type of magnetically shielded room, for example, in our site, costed like €500,000. Okay, so just to give you an idea of the type of cost that these kind of things might have. So just to give you an idea of the history, as I said to you before, the first superconducting magnetometers was the first data with superconducting magnetometers was recorded in 1971, 72, and obviously published in that year at MIT. And after these first recording, different type of labs in the world started collecting the data. Still in the 80s, like you can see here, most of the studies were conducted with 1 or 2 channels. As you can see here, for example, from this depiction, the technology was quite rudimental, or let's say not very developed. And they were mainly recording the data at night, so that there was much less noise, because people were not like, moving and driving. Then we moved in the 90s to systems that considered a higher number of channels, like the one that you can see here. We were in the range of tens or 100 of channels. This was also due to the fact that the technology for the sensors was like way better, and so they managed to reduce the dimension of the sensors. Nowadays, we have systems that are the one that basically were developed in around the 2000, 2005, 2010, which are MEG systems with around 300 channels, more or less. Here you see one example of a normal MEG similar to the one that we have here at CIMEC. Here you have a specific type of MEG. This is a fetal MEG. So it is, there are very few in the world, so I'm just introducing it for you to have a complete picture of the technology. I think there are 5 or 6 in the world. People, so pregnant woman, will basically put the belly here with the fetum, and you can record the activity from the brain of the kids, obviously, while they are still in the belly of the mother. And this is like a specific type of application of MEG, but just to give you the full picture. So normally we are interested much more in the normal one, in which the participant is basically sitting and doing some cognitive task. In this case, what you do, for example, in the case of the studies with fetus, what you do is to provide some auditory stimulation and see if there is a response, for example, okay? So just to give you the full picture, this is the system that we have at our center. This is state-of-the-art MEG. We can record MEG signal and EEG signal at the same time. We will see why this is important. As I told you before, we can not only record the data while the participant is doing some behavioral studies, but we can basically turn the MEG down and do also sleep studies. In our center, there are people interested in sleep studies. What you do is you take people, you make them sleep during at night, and you record the data. So it's also like another type of studies. Normally you look more at the continuous activity that you can record, doing like some analysis that are more similar, for example, to resting state. In addition to MEG or possibly EEG, you might also record different type of external data, like electroculography, electromyography, electrocardiogram. And in addition, you can at the same time record other type of information. There's a very new wave of studies, for example, that use the MEG in order to study, for example, speech perception. So how we understand while other people talk. And in this case, what they do is to use continuous stimulation. So you will hear, for example, a story, and you can record the information that are coming from the auditory system into the MEG, and then compare how the brain changed with respect to these, for example, stimulation. So MEG and EEG are very powerful also when we want to understand how the brain might represent stimulation that are continuous and very complex. We will come to this later on. As I said before, this is the type of sensor that there is in our machine. Actually, each of these square here comprises 3 different sensors. And as I anticipated before to you, there are different type of sensor in different type of MEG. In our MEG, we have magnetometers and gradiometers. We have 200 gradiometers, 100 magnetometers, more or less, so 300 sensors in total. In our machine, there are other type of sensor, which are called axial gradiometers. So in blue, you see the type of change in terms of magnetic field, so magnetic flux, changes that are captured by these sensor, which is different. I don't want to go too much into details of that, but the point that I want to make here is that the sensor that we have in our machine capture different type of signal. So this type of planar gradiometer, in the way that is constructed, tend to record activity that is below the sensor, so mainly related to the cortex, whereas this type of sensor, magnetometer, can record also information from deep sources. So this is the type of sensor. So here we have magnetometers, and here we have the gradiometers. And the type of magnetic field modification that they capture is different. Here you see, for example, the same activity that we simulate in the brain. And here you see how it is basically recorded from the magnetometers, and here it is recorded from the gradiometers. Why I'm presenting this to you? Just to show you that the type of information that, as I said before, you can record from MEG is very complex and might be slightly different from one MEG to the other. And even in the same MEG, in this case, you have 2 different type of sensors that record slightly different type of change into the signal. As I said before to you, in our MEG, you can record not only MEG, but you can also record at the same time EEG in the same participant. So I took just a random study on the internet, which actually collect data with MEG, so with these 2 type of sensor, and with EEG. So we have the same data recorded from these 3 different type of sensors, and we see that the topography of the same activity of the brain is different. So why I'm showing you this? Because I'm wanting to tell you that it's very important that you know what you look when you read like EEG or MEG study, because the same image might mean something that is very different, okay? In this case, we have 3 different conditions related to word processing. I think I was not very interested in the type of task, but let's say you have 3 conditions, and you can see that there are differences if you measure it with EEG, also at the level of the gradiometers and also at the level of magnetometer. But the topography of the signal is very different. This is why it's important that you know the type of signal that EEG and MEG record, but also the type of sensor that the type of MEG you are using is basically implemented in that MEG, okay? And so the good things about this MEG EEG is that you can use all these signal to make source localization. So as I told you at the beginning, to see which part of the brain might be basically originating this type of signal. And in this case, you can also compare them. What I wanted to show with this type of figure is that you cannot directly compare EEG and MEG because they basically record different things in the brain, and this is evident when you see these and these. These are the same participants, same stimulation, what at the same time. Simply what change is the sensor that is basically recording the data, okay? And even in MEG, it's important that you know what type of sensor has been used or which sensor is shown in the paper to show you the results that you are looking at. So this is why I think it's very important that when you define what you want to do with MEG, okay, so the original question that I told you is that you have in mind already what you want to test, because there are so many variables in the signal, in the type of analysis, but also at the level of the sensor, that it might be very difficult to understand what aspect of the signal you want to study in your specific type of research. Normally, what I always suggest you is to go back and see what other people did and try to first replicate what they did and see if it is there, and then start from there to do your own studies, for example. And also, as I said at the beginning, consider if you really need MEG. Sometimes you might not be needing MEG, and other type of approaches might be better. So just to show you, 7 years ago, there were more than 150 MEG in the world. So as Javi said at the beginning, yeah, most of them are located in North America, Europe, and also in Japan. Nowadays, I think we are a bit more, probably around 200 or something like that. And this is just to give you a rough idea on the people in the lab in the world that work with MEG. So this is like a small community, relatively small with respect to fMRI, for example. And why this is the case? First, as we will see soon, is that an MEG costs quite a lot of money. So normally this type of machinery is purchased only in specific type of research center that are interested in doing MEG research. This is just to show you more or less how it looks our lab, to give you an idea. So this is the MEG. Everything within the seeded room needs to be not distorting the signal. So for example, in this case, we are using some fiber optic response box. You can see that here we have a panel. There is not video inside. There is a projector outside the seeded room that project inside the MEG, some type of stimulation, and the participant that is basically dressing, is basically removing all the dress and all the possible metal part, like chains or rings and stuff like that, is basically positioned within the MEG. As I said before, it's even more important in MEG than in MRI not to have the any kind of metal, so that you don't have any type of noise in the data. If there is a participant that, for example, have some piercing or stuff that forget to remove, you already see it in the data because there is so much noise that you don't see anything. And so you understand that the participant, for example, entered the room with something metallic on it. As I said before, you can record different type of information from the sensors, and in parallel, you record other type of data. This is very important because you can relate external information to the brain and also internal information to the brain. We will come to this in next lecture. And this is just to show you that with respect to fMRI, we need a very high precision in the stimulation stuff that we have in the lab, for example. So the precision that you need to have is at the millisecond level. Whereas in fMRI, as the signal is much slower, this precision is not needed, okay? So in our case, for example, we have a different type of stimulator. We have an eye tracker that tracks the eye movements, which is MEG compatible, which we basically, at the same time, while we record the MEG, we record the eye movement in order to relate the two. And then we can use, for example, MEG for neurofeedback. So we can use the activity of the brain, do the analysis online, and, for example, present some type of stimulation at specific time point. Or, as I told you at the beginning, you can even stimulate while you're doing MEG. So in the last part, I want to try, or I try to compare MEG to other type of techniques that you might have seen. So as I said before, the temporal resolution MEG is very high, so it can go up to 1 millisecond, whereas other type of technique has much more quartz temporal resolution in terms of second, for example, of fMRI, or even later in terms of petrospect. The spatial resolution is much higher, for example, of EEG, and potentially, but not always, could even reach the spatial resolution of the fMRI. It's not always this the case, but there are specific examples that I show you in a second that seems to suggest that this is potentially, so the limit might be very, very low and lower than the one that we might think. So first comparison, I think, is important to compare MEG with EEG. So people could tell you, okay, MEG has only advantage with respect to EEG. Why don't we have an MEG in all the center in the world? The answer is here. So an MEG system costs 3 million euro, and this is a lot of money. So a good EEG system with 64, maybe 128 channels might cost around 50,000–60,000 euro. So you understand that the difference in price is great. And this is why EEG is much more common than MEG. In terms of temporal resolution, they are basically similar. In terms of spatial resolution, as I said before, EEG has a intrinsic spatial resolution that is higher than MEG, because the signal that is recorded by EEG, so the electrical signal originating from the brain, is distorted. And this distorted can only be partially accounted by the model that we use to estimate the origin of the signal at the level of the brain. Whereas MEG records magnetic signal that is not distorted. And this is basically the main or most important aspects that makes MEG better than EEG. So the second big difference that we might want to consider is to compare like MEG and fMRI. So I normally don't see them as in competition, but I see them as I told you before, as complementary. So in my lab, I'm doing both fMRI and MEG studies because I think fMRI is very good for answering some question I have, whereas it's not good to answer some other question where MEG is perfect, and vice versa. So one aspect that I think is completely clear at the moment is that there are specific fields in which MEG might be much better than fMRI and vice versa, but the possibility to combine, so to study specific type of topic using both fMRI and MEG together, maybe also in the same participant, is the way for the future to go. Because in this way, we will basically use the stronger points of fMRI and the strong points of MEG together. So as I said before, there is a strong difference in terms of resolution, as fMRI has a resolution of seconds. Yeah, if you already encountered fMRI before, you know that the signal that is measured by fMRI, normally blood oxygen level dependent signal, so bold signal, is very slow and peaks after 5-6 seconds after the stimulus or the stimulation. So you cannot go below that. And bold signal is not directly related to brain activity. It's related more to metabolic activity and to blood flow. Whereas the signal of MEG is in terms of milliseconds, is a signal that is related to postsynaptic potential mainly, and particularly to the changes in the magnetic field induced by the current of these neurons. So it's much more related to activity related to the brain with respect to the bold. The temporal resolution is in terms of milliseconds. We can see the change in time. fMRI, depending on the type of scanner you have, you can go even below 1 square millimeter. If you have a 7 Tesla machine, for example, you can do what is called the laminar fMRI, looking at specific brain layers in specific part of the cortex. The spatial resolution of MEG varies a lot. Let's say that if you don't have any anatomical image of the subject, you are in the range of 10 to 5 millimeter spatial resolution. If you have the anatomical image of the subject, any specific situations, you can go below up to 1 millimeter. That is basically possible, but just in specific type of situation. In general situations, you are lower with respect to EEG, but still higher than fMRI. With respect to cost, as I said before, MEG costs 2-3 million, but whereas fMRI costs around 1 million per Tesla. So free Tesla machine as the one that we have here. We bought a new one, top of class, Siemens machine 3 years ago for, yeah, more or less 3 million euro. The point is that with MR scanner, so a magnetic resonance imaging scanner, you can do not only fMRI, but also a lot of other type of images. This is why MRI scanner is much more widespread adopted, and also because it's used in the clinical setting. MEG is used not much in the clinical setting. It has some applications for let's say, localization of epileptic focus in patient, but that's not its main focus. So it's more like a machine that is used just for research. As I said before, there is quite a huge discussion on which is the spatial resolution of MEG, and this study really pushed the idea of trying to understand what was the limit, and what they did was to make specific type of restraint. So they made MR image of the participant. They created a 3D model of the head. They constructed a cup in plastic with a 3D printer that was subject specific, which you can see here. And the participant was inside the MEG with this cup, so he could not move the head. In this way, there was no head movement, and that should be discarded in the data. In a specific study that used also in addition to that approach, they tried to understand what was the limit of MEG. They showed that they could basically record the activity from the more deep and external layer of the cortex. In this specific case, what they did, they segmented the anatomical image and they also looked at the activity within the motor cortex, so very strong activity that we know where we can localize, and we had specific type of end restraints that we seen before, and they could show that there were differences between the deep part of the cortex and the more superficial part of the cortex. As the cortex has a range that is several millimeters wide, they could show some type of differences between the two. They said that probably this would be a study that demonstrates the limit of MEG. So as I said before, it seems that it's possible to go down to millimeter resolution also in MEG, but just in specific case and not always, okay? I'll do my last lecture, my last slide, and then we continue next time with the future of MEG. So a few years ago, like 4 or 5 years ago, when I was presenting this slide, I was stopping my lecture here because I was like presenting what is the future of MEG. So one future would be that now we have around 300 sensors, and the idea is that we can make smaller sensors and go up to 500 sensors. There are some let's say prototype of MEG with so many sensors, and this seems to be one potential application. There is people that try to put together MEG and fMRI. So we have an MEG with a small, which seems theoretically not possible, but it is if the MRI is a low field MRI that can give you some information in addition to MEG. And then I was talking about these optically pumped magnetometers. These are magnetometers, so MEG sensor, that do not need the liquid helium to work. So the technology is completely different. And this is the example of one of these sensors. And the idea 5 or 6 years ago was that this was the future. But the future is now, basically. And next time I will show you that there are studies that use these sensors in order to probably develop the new system that will basically replace the squid-based MEG in the future. Okay, I think it's time. So it was like quite intense. So I'm stopping here, and if you have any question, we'll be happy to answer them. If not, at the beginning of the next lecture, you can also have some question to me, okay?
Okay. Do you have any question now?
Oh, okay, sorry.
We can ask next lesson.
Okay.
That's okay?
Yeah, great.
Thank you so much, Luca.
No problem. We see each other on Friday, right?
Yes, at the same time.
Okay, great. Perfect.
Digan
So have a
ciao.
nice day. Ciao, ciao.
Ciao Luca, ci vediamo, grazie tante.
Ciao a te. Ciao.